tonight a very exceptional speaker who has a seriously long list of background history. Prior to his current role, he was the Chief Technical Architect and Global Head of Enterprise Computing for Morgan Stanley. He was also the Chief Architect, Global Head of Architecture and Engineering for Bank of America Merrill Lynch. And the list goes on. He was systems engineer in the aerospace industry and for the CIA. No joke, guys. So please welcome the CEO and co-founder of 60 East Technology, Jeffrey Birnbaum.
I don't know if I'm going to need this mic, but let's see. So, thanks for showing up tonight. How many of you came to get free stuff? All right, somebody's honest. How many of you came because of that sexy title? Okay, one, two, a couple. All right, well, hopefully we won't disappoint. We're going to show you a couple things that I think that will make the title seem real. We didn't just make it up. Although, I mean, many of us wish we could have a time machine. I remember as a young kid reading H.G. Wells and thinking how cool it would be. But then you have to figure out, well, where would I go? How far back would I go? I guess I like living in the present. So here we are. Actually, can you go back to that one slide? Go back one slide. So that, if you didn't see the resemblance, that is the T-shirt design. That is a cool picture. Designed by our co-founder, Brad Hunt. The brand is here tonight, and maybe when we get to the questions, he can come up and take it through. Another member of the team here is Dirk Myers. He'll be helping me get through this presentation. I should warn you, so most presentations I do off the top of my head, and I use very few slides, maybe have a couple slides. This deck is 51 slides, which is crazy. Now there's some animation in there. So I've never done a deck of 51. So that'll be the first time, and it doesn't feel like 51 anyway. So let's go ahead and go. We're going to talk to you about AMPS and all of the things that you could do with AMPS, which is analogous to what you could do if you had a time machine, at least a software-based time machine. And I hope by the end you'll see what I'm talking about. Let's go to the overview. So this picture is our best graphical rendering of what AMPS is. So, you go to many of you programmer types, you go to a cocktail party and somebody says, hey, what do you do? And it's like, okay, if you're not a techie, how do I explain this to you, what I do? Well, sometimes that's what we feel with AMPS, because it does a ton of stuff. And it's not just one thing. And it's a couple of things. And it's a couple of things because most applications that you want to build don't just want one thing. They want messaging. They want some form of state management with the database. They want some type of aggregation capability where I can aggregate some of that data to reduce it. Okay? They may want to go back in time. Like, what was the state of something a little while ago? And when you do all of those things separately, they don't tick together, if you will. Right? So you could do your messaging, but if it's not coherent with your database, and you're an application writer, and you tap into the stream, and you do queries in the database, how do you join those two things to make sense of where one ends and the other begins? So you can go to the database and sort of get the state, but where does that state, what's the meaning of that state relative to maybe some real-time stream that you have? So what we've tried to do in AMPS is take all of those things, database, pub/sub, aggregation, and make them all tick together. To do that, we've had to build an extraordinarily scalable system. And even though I'm not going to give you charts and charts and charts of performance, we'll leave that to you to take away and maybe download AMPS and to kick its tires, because you will not believe the performance. Even when you run AMPS on a VM, you will see incredible performance that you cannot get in most other systems. And it's actually embarrassing. Recently, we were asked, how does AMPS scale? That's always the question people want to know. And if you add more subscribers, does your performance go down? What happens? So we went and benchmarked AMPS against some open source stuff. And let's just say that it was a slaughterhouse. Not only did it kill it in performance, but it did the thing that very few software entities do, which is on the system we were comparing to, as you pushed it harder, the time got further and further out. So if you started with a scenario where you had one publisher and 6 subscribers, and then you went to 12 subscribers and then to 18, the performance just ratcheted up. It got worse and worse and worse. With AMPS, we started at 6, and as we ratcheted up to 12 and 18, in a fan-out perspective, the performance actually got better and better and better. And somebody asked me, well, how do you explain that? I mean, that's bizarre, right? Things don't get faster as you load them heavier. AMPS is one of those rare beasts where, because it's so fast, because it's so highly tuned, okay, as you push it harder, it sleeps less. And therefore, it actually is faster. And at some point, it will break, obviously, and then the performance will go up. I mean, I'm not trying to say it just keeps going down. But it doesn't observe the normal phenomena that most applications do, which is very important when you try to do these things. So, for example, when you try to combine a database with a real-time messaging system, and somebody does a query, and let's say that you were naive and put a global lock in there to maintain the state to get atomicity, then where's the pub sub? The pub sub just sort of comes to a stop, right? So we've done a lot of work in AMPS to make it so that pub sub, database queries, all of these things flow together well, and we don't have any of these types of large pieces of jitter hanging around. Okay, so I'm not going to spend too much more time on AMPS other than walk you through an example of usage, okay, that kind of resembles some of this time machine idea of how we do this. So let's go. Let's start it. So this is a typical, what we're going to do is we're going to walk through a set of slides that show you an application. And what we did was we constructed this hypothetical taxi cab application. Because believe it or not, if I was a management company managing a fleet of taxis, I might want an app like this for my potential customers or for how I manage my own taxi fleet. So what we're going to do is we're going to have each taxi. He's going to publish his data, his location, position, whether he's hired or not hired, or he's available, etc., to AMPS, and then you're going to have views of that, which are clients that are connected, mobile phones, whatever they do. So we're sending out, through subscriptions, each one of these is subscribed to the universe of taxis. Now immediately there's problems here. So if I'm in New York City, and I'm at 6th and 50th, do I want all taxi cab locations? Probably not. So you need a way to filter that data out. So let's go. So here's the classic problem. We have, I think there are 13,500 and something taxi cabs in New York City.
14,600.
Yes. We know this because we're actually building this demo. Okay, so this is slideware of the demo, but we're actually building this demo. So we know these details. Okay. So we have all these cabs, they're all publishing, and really think about if they're updated once a second. It's 14,000 updates a second. It's pretty small potatoes, it's not very fast. Okay? But then you've got potentially a large fan out. So fan out is very important here, right? And imagine now if everybody's getting every location, you're getting 14,000 updates a second. 14,000 times, let's call it, 1,000 phones. Let's say there's 1,000 people that are looking for cabs or looking at this data. That's a lot of updates to be pushing on the network. Not a good idea. That's where AMPS comes in. Okay? So this is the picture where you see all the cabs on the grid. And this is what, if you were getting every location, imagine your phone is sitting there getting all of this data, and in 5 minutes it's dead. Right? Because it's just doing too much. So what we do is we introduce the concept of content filtering. Okay? And content filtering is a SQL where class. I'm interested in all taxi cab updates where they're in some radius, right, around where my latitude and longitude are. Okay? So this is what your app is going to do. It's going to figure out from your phone where you are. It's going to build a little radius. It's going to say, hey, I only want to subscribe to that stuff. And as taxi cabs move and change the location, things are going to come in and out of that view, right? And just hold that out for a second, because that's an interesting thing that most pub sub systems don't do. Okay, so slides here. So we've got this content filtering, where we've got AMPS taking this. Every phone now is only getting the updates relative to them. So you've automatically shrunk the problem down. You've added usability to the phone because now it's not getting tons and tons of stuff. It's maybe getting 10 updates a second because there are 10 taxi cabs. Okay? Let's go ahead. So this is now the view. So when you first got your phone and I was giving you everything, you looked at the view, that's what you saw. Now we've narrowed this thing down, so now that's the view we can get. You're at some location in this vicinity, okay? And you say, oh, there's a lot of cabs around. Or I can see that there's maybe more on 2nd Avenue or some other avenue. Let me walk over there and try to hail it. It would be awesome if you could actually hit a hail button, but we're not selling an app today. We're just talking about how we could build an app that does something like this. Let's go ahead. So AMPS has, as I mentioned, we already talked about PubSub and content filtering. Okay, the next thing that AMPS does is I like to call AMPS the AMPS database that we call State of the World. Okay, I like to call it the State of the World. Okay, because what we're going to do is it's going to be a NoSQL SQL database, and I don't mean not only SQL. I mean NoSQL in the sense of an object. So in all of these NoSQL implementations that were the not only SQL variety, what they said is, we're going to store an object for you, and you're going to have a key, and you're going to come and get that thing. So we add to that SQL. So now you can have all these objects stored, okay, and you can come and get your data via a query. And the keys are interesting because our keys are more like a primary key in a database where you choose which fields, or most people refer to database columns, form the key that makes an object unique. So let's say that you were going to do something like stocks, right? You could say the symbol is uniqueness. And then you'd have a last value cache for all stocks. Okay, that may not be interesting. Okay? Now AMPS has a second dimension that it adds, which is, and we're going to show how this can be used, which is now add history. Okay, so now say IBM ticked at 100, and then IBM ticked at 105, right? Okay, those are two different updates, and I may want to store those as a history. Okay, so not only do I get object at 105, but I retain object at 100. Okay, so we can do more than just overwrite the last unique thing. We can actually retain history as well. We are not, I will make this clear, we are not a time series database. Okay, and we'll show you how useful this is. So we have some concepts around this data in terms of how much history to actually store. Again, we're not trying to be a time series database. That's an entirely different thing. There are whole companies designed for that. But it is very nice. And in this particular case, because you're only doing it once a second, you could retain, say, a full day's worth of history pretty easily, right? And then be able to call back, right, taxi cab locations at any point in the day. Okay, so I want to do my query as if it was at 2 o'clock in the afternoon, and maybe it's 5 o'clock now. I can see where all those taxis were at that moment in time, which is pretty nice. Right? That's a different dimension to the database. Now, in addition, what I didn't talk about was the other thing that we do in AMPS, and I sort of saved this. Okay, so what are the 3 things we do? How many can name them that I've told you about so far? Come on. PubSub, okay, database, and aggregation. Okay? We do something else, which is called a transaction log. Our transaction log, we actually hold it out as a separate entity. It is not a transaction log to support a database. It is a first-class entity that you can use in your application, just as if it was itself a table, right, or a topic that you can query. You can query the transaction log with the same exact SQL semantics that you're using, right, for your tables or your topics that have these state of the worlds. Okay? So now you have this interesting thing. You have a transaction log that's sort of, we like to call this the flight recorder. You're recording in time order everything that comes into the system. So think about it from a queuing perspective. It's like a large, deep queue. Okay? Every location in this transaction log has an associated bookmark. A bookmark bookmark is just simply that place in the transaction log. And if you have one of these bookmarks, if you're so lucky, okay, you can say to AMPS, hey, I want you to start sending me all of the data that match my subscription, but I want you to start right from this bookmark. Okay? Somebody's doing something. That's screaming? Anyway, so what we're showing here is we're showing a bunch of time series updates, okay, that are stored in this state of the world and also stored in this transaction log. And one of the cool things we're going to show you, right, or hope to show you, is how you can actually use the transaction log in conjunction with the state of the world to do something like the following. Show me all the taxi cabs where they were at 2 o'clock, and then start that flight recorder and send me every event post 2 o'clock so that I can then map out how every taxi cab dispersed through the city for the next hour. Right? So I can get their path. That's pretty cool, right? And we're going to show you why that's useful in a second. So let's go. So we're going to show a historical replay example. So let's move forward. So we start with this scenario, a bunch of taxi cabs in a location. Okay? All right. So one of the things that we're going to show here is we've got 2 taxi cabs that are on the periphery of your radius. Maybe you're in the middle of this thing. Okay, now so time advances forward. Now go to the next slide. Okay. One of the things that we do that's different than most any other pub subsystem, okay, is that if you send a subscribe command to us, say, hey, I want all the taxi cabs that are in this location. It starts sending you updates, okay, that get all of those. Now, if a taxi cab goes out of that vicinity, I mean, for whatever your query is, you don't get an update. That makes sense? So you had a taxi cab that was in your region, but you're not going to get an update for him if he moves outside the region because he's no longer in the region. He's not matching anymore. So you're not going to get an update. How do you solve that? So that's where this concept of out-of-focus processing comes in. When you make your subscription to AMPS, you can optionally say to AMPS, hey, this is what I want, and I want you to send me out-of-focus events. And what an out-of-focus does is says, if this update to this thing, okay, causes the object that you have to no longer match. So it's the opposite now. So it used to match, it no longer matches, I will send you a special out-of-focus event. How cool is that? Right? Right, so I'm sitting here, and now these 2 cabs, right, that are on the periphery, the next update that you see, they're gone. Okay, that's hard to do in a traditional pub subsystem where you're only getting updates that match. Because you would not get updates for those cabs. Because they're updating outside of the region. So you've got this static screen, and they're like stuff. It's like a blotter that has a ticker or an order that goes from open to closed. And your subscription says, give me all open orders. So you're getting all the open ones. But what happens when one of the opens goes to closed? You'd have to have another subscription, right, which is a pain in the butt, right, that says, give me all the orders that go to that are closed. And then you'd have to merge and figure out, oh, one of those is on the screen, I got to take it away. So that's what this out of focus does for you. It's another part of the event stream for your subscription. Let's move on. Now, here's where the state of the world becomes a very handy feature. So what we showed you earlier was, I'm sitting there, I've been getting updates for the last 10 minutes, so here's my picture. I'm a current subscriber. I'm getting all these updates. Now, I come into the mix, okay? I come into the mix, and I say, hey, I want to put in my query, okay? Well, no updates. Let's just say that a second is an extremely long time for you to wait. You can't wait a second. You operate in microseconds. Well, you're going to sit there for a second before you get any show on the screen, okay? However, in AMPS, what you can do is you can say, hey, I want to do a query and a subscribe in one atomic command to get my current, all those positions, and then as they start updating, send me those updates as if I subscribed. So if you do that, boom, you get an immediate. Now this is not that great, for time scale of a second when it's a human being, but imagine your code and you would be a full whatever behind. This is a flash of the state, and then bingo, you're right up to date. Okay? So that solves the late joiner problem. The late joiner can come into the system and get right up to speed with where he wants to be. Okay? Without having to wait for all these updates to appear. Right? Make sense? Anybody confused? No? This is awesome stuff? Yes.
So what
It
you're
is.
saying, what you're saying makes a lot of sense, but what you're telling me is that current systems don't do this?
No. You can make systems do anything. I'm just saying that AMPS as a system, advanced message processing system, okay, has been designed to make it easy to build applications that do these types of things. Okay? You can stitch together all kinds of stuff. You could do the out of focus, but you'd have to do it. You'd have to write the code to do it. We're providing that out of the box. It's already well thought out in terms of when does an out of focus come versus when does it not come, all that stuff.
Okay, so it's all taken care of.
Yes. Remember, what we're trying to do is build a piece of middleware that you can use to build applications. So we're trying to solve a lot of different problems to make it easy to build systems. Okay? I can't build your system for you, but I can give you a piece of infrastructure that lets you actually create interesting applications. Okay? There's an infinite number of those. There's an infinite number of ways to build them. Okay, next guy. So now we're going to talk about a historical SAO, and I already sort of primed you a little bit. So what we're talking about here is I show up at some point in time, and I want to say, hey, where was the cab at, say, 2 o'clock? And then I want to see how it progressed, okay, throughout the day. So if you had an ordinary database, the only thing you'd have is the last position. Okay, but here, I can go get the state of all cabs. So this is the important part. I can go get the state of all these cabs at a moment in time, because I'm using this historical feature of the database, okay? And then I could start a replay from that moment to actually replay their paths, and we'll see how that is in a second. But just imagine that for a second. I'm doing a query to the database, and I'm saying, hey, go back in time. Go back to an hour ago and give me the state of every cab. Most databases, you only get current. Give me the current prices on these stocks. Well, what if I want to know what were the prices an hour ago? And I want to know them in a consistent way. So I want to know IBM as it relates to the moment in time that Intel was at a certain price, right? That's a slice. So we're doing that as well with this, which makes it pretty incredible. Okay, let's move forward. So let's go to the proverbial example that we want to talk about, which is I lost my cell phone. Or I get out of the cab, I step away from the cab moves away from me, and I start doing this. Oh my God, I left the phone in the cab. Right? If it hasn't happened to you, maybe I don't know, you don't have a cell phone. It hasn't happened to me recently, but it has happened, and it's exactly the same feeling every time as the taxi pulls away. I can't make out the number on the cab, and I'm like, oh my God. But I do know a couple things. I know where I got picked up, right? Approximately what time I got picked up, potentially, okay? And I know where I got dropped off and approximately what time. Hopefully I have a watch, right? And on my phone, so I don't have at the time, but hopefully I still wear a watch. All right. So this is what happens in this particular example. We call up we move to that slide yet? We go too far ahead already. Go to the next one. We call up the cab company. Okay, these are our two locations. Sorry. Okay. So we got our two locations, where I got picked up and where I got dropped off. So with some degree of accuracy in terms of position. Okay? Let's just assume that when I call this taxi cab company, I can give some coordinates and they can translate those to latitude and longitudes. I was at 6th and 50th, and I got dropped off at 79th and York, something like that, right? Approximately these times. Okay, so I do that. So what we're going to do, okay, in this particular example, is we can call this proverbial company that's managing this fleet of cabs. I can tell them, okay, approximately where I was, what time it was. They can do a query from the database at that moment in time. They can do a query from the database at the other moment in time. Find the collection of cabs that were in the vicinity, okay, around that time, okay? And then, of course, you can take those two, do a little set theory, and figure out which one it might be, okay? And have a shot to actually call that cab and get the phone, okay? So that's some of the things that you can do with this technology, which make it pretty incredible. To do that, to build that app, if I told you, if any of you guys are probably great developers, some taxi cab fleet manager called you up and said, hey, I want you to build me an app, okay? Okay. The first thing you're going to do is, God, I saw this cool thing, AMPS, I'm going to go grab that and I'll build this app, right? And I'll have it for you this weekend, and hopefully you get paid a lot of money. Okay. But the amount of work you have to do to build that app, so you have to set up a database, you have to do this, you have to have a query ability. What do you do? Very historical. You're going to save that off. You're going to snapshot it every 5 seconds, so you have some history, whatnot, right? Not only that, once you do this, and now we've got the taxi cab, we can use the transaction log, right, to show us where that cab might be going now. Like, what's the path? Where is it going? Because we're basically recording, right, in the transaction log, the movement of that thing. So, what could you build if you had this type of tool? Okay? I think you can build all kinds of stuff. Hopefully we've given you a glimpse, right, through this taxi cab demo, or slideware demo, of the types of things that AMPS can do, okay, for the apps that you probably want to build. So again, we're going to do a wash, rinse, repeat. You got a first class, and I mean first class pub subsystem. Okay? We have a NoSQL SQL database that has one additional dimension. It has historical capabilities. Okay? You have the transaction log to record every event, to be able to get arbitrary replays of your data, and the arbitrary replays are filtered. So it's like, doing a cat on a file is not very nice. Doing a grep is much better. Okay, and that's the analogy here, is that when you have a content filter, you're doing a grep, essentially, but a structured grep across the content. So you've got JSON, for example, or your messages. And I want to be very selective about the messages that I actually get. Okay? And then I didn't talk too much about it, but aggregation. So we can do joins, real-time streaming joins, which is an incredibly difficult problem. So for those of you familiar with products like Streambase that do aggregation, one of the ways they do aggregation is they use these concepts called windowing, which they'll tell you are awesome techniques. The only thing is, we do window equals 1. Every message gets done. That is incredibly difficult to do. Imagine the number of things you have to do as each update arrives. Okay? You're looking at me with skepticism.
Yeah,
you should have skepticism.
I know the process. It's taking 2 streams.
That's correct.
Making them up.
That's correct. You know how difficult it is.
You know what a jitter buffer is?
Yeah.
It's very similar.
And you'll realize how unbelievably awesome this technology is. Okay? So I only scratched the surface of the types of things we can do. I didn't talk about the actual app itself, or the application itself, AMPS. AMPS has been built from the ground zero, as you heard in C++. It's ridiculously programmed for performance. We're big believers that this proverbial 80-20 rule doesn't necessarily apply. And the reason it doesn't apply, I mean, it's sort of a nice general rule that you should only focus on, the problem that matters. The problem is when you try to build a system like this with all of these components, every piece of it matters, and every extra CPU cycle you use matters because you're stealing CPU cycles away from another part of the system. This is not a single-threaded system. This is heavily concurrent. We're doing a lot of things all at the same time. Okay? We have scaled this thing up. So we recently ran a test. So it's a ridiculous test. Brand actually ran it. He can tell you a little bit about it. We ran it on a system that had 6 terabytes of memory. Okay? and 320 cores. Okay, and we were running a query on a table that had 1 billion objects in it. Okay, and it took I don't know 5 seconds to run the query that had a like expression. So imagine this: you do a like, which is a regex, on 1 billion objects. Okay, and we returned the result of that query in 5 seconds. Now, 5 seconds seems like a really long time. Do the math on the amount of memory that you have to touch. There's no database in the world that's going to be able to do this in that kind of time. And the reason they can't do it is because you're doing a full table scan. There's no index in the world that's going to help you with that. That is a full table scan. I think the database took 2 terabytes of memory. Yeah, 2 kilobyte messages. So we're moving around, and when we look at the profile of it, it's completely memory bound. So we are going at the fastest speed you can go at. You just can't go any faster. Although we probably think there's probably some tuning we can do in Numinous for it. So it's been programmed for scale. Scale, performance, latency all interact in some weird way. But we scale up and scale down. You don't need a monster machine to run this. We run every day, and people run every day in VMs with very little resources. So when I say it's been ridiculously tuned, it's been ridiculously tuned up and down. So you can run it in a very small footprint. Okay? How much you can do depends on how much resources you have. And we will use the resources that are available to us in terms of getting stuff done. And I think there was a trivia question, how many messages can you filter or whatever per core? Per core, it's easily over 1 million per core. We're doing some stuff right now, performance testing, where we're doing some large fan outs, where we're doing flight recording of 1K messages we're doing at an incoming rate, an ingress rate of 350,000 a second. We're recording that to the transaction log, and we're fanning that out to 12 subscribers that are getting every message. And the most interesting part of that example is when you do the math on the networking capacity you need, you will tip over most networks doing that. And we push it about to its end. I think it gets, that particular example got to 38.8 gigabits per second, or was that 5 12-byte messages? What?
You're right.
Yeah. So we pushed a 40 gigabit NIC to its knees. And AMPS was keeping up. When we look back, we can see that it's pushing not at all back on the publishing. That means that basically we're ingesting 350K, 1K messages per second, which is just incredible. Now, I wish it was 1 million. I'd like to get to 1 million. The technology on the storage side is not there yet, but it will be in the next few years. And with that, I think I'm going to ask Eric to come back up. Eric.
Before we move on to Q&A, I just want to give a great big round of applause, Jeffrey. Birnbaum, and we'll start taking questions. By the way, there's plenty more drinks and stuff, and we have T-shirts at the end of the questions. We will be giving away to everyone who wants one. We have plenty of T-shirts. They are awesome, and if you like the DeLoreans as I do, they have one right on the shirt. So let's take the first question. Right there.
I like the taxi project. I have one question. Is there public API for getting the real-time data?
Public API for
For getting the real-time data?
real-time data for what?
For the taxis?
Oh, the taxis? Brad? I think we're
We're
getting
gonna
simulated data.
demo and we'll probably do like a behind-the-scenes thing because it's actually a pretty cool project. Everybody wants taxi data, but even our competitors want taxi data. But so we'll probably do like a behind-the-scenes like kit that allows you to replay the data that we use in the demo. So just follow our news.
Yeah, we're actually building this actual demo. We are building this. We are building this exact demo, and it's going to be super slick with super slick graphics, the whole thing, but powered by AMPS.
Okay, so it hasn't done yet.
No, it's not done yet.
Not done yet.
Thank you.
Come on, follow us on Twitter and stuff. You'll see it when it comes out.
But you'll be
producing simulated data, not actual, you haven't outfitted 13,000 taxis.
No, this is a demo application.
Okay, fine.
Yeah.
Right.
It is simulation. That's
I'm sure if some taxi cab company sees it, they'll come knocking on our door saying, we want to buy that. We're not actually in the demo, we're actually not trying to produce a taxi cab application. We're using it purely for purposes of demo to show what you can do with AMPS.
What is your target, I mean, sorry, taxis, what's your target? Where do you feel the biggest bang for the buck right now with the, in terms of application? I mean,
Oh, I think there's a myriad of applications that are untapped. I mean, you can talk about sensor data that's coming online. I mean, in financial services where we currently are, that's our bread and butter, the technology of AMPS came out of what people are trying to do in the front office of financial services firms. They have data that's flying around super quick. They need to be able to store it. They need to query it. They need to get real time. They need to aggregate it. They're going to get some P&L, some positions that are being aggregated in real time. And they're always frustrated because, like even position management, it doesn't tick when your data ticks. So your blotter changed, and you're looking at your P&L or your position, you're like, but it's not updated relative to the trade I just saw come through, or the order that just got executed. Right? We're trying to tie it all together, which makes it pretty incredible. But there's a myriad of applications. The taxi demo is just something we came up with. We were sitting around brainstorming one night in Vegas, which we probably should have done, and we brainstormed this application.
Can you give another example in a different context of the late joiner problem?
Of the what?
Of the late joiner problem.
Yeah, it's a simple one from finance. So I'm sitting on a desk, I'm a trader, and I'm watching a set of accounts, right? And there's all kinds of orders executing, and my buddy over here says, you know what, can you watch my trades? Now, this would never happen in the real world, okay, because unless they're in the same group. Says, can you watch these accounts for me? I have to go to the restroom, I have to go do something, right? And you say, okay, I'm not at his computer, so I get my computer. I switch to his accounts, I do a query that says, hey, show me all the open orders in these accounts. And boom, the state just appears. Now those orders may have been sitting there for a little while, right? And that's an absolute example of SAL, state of the world, and subscribe.
So you wouldn't have to download all of his other orders. You would just get the ones that you want.
No, that's the whole content filtering example, which is I'm going to be very precise. I only want orders that are in the open state and they're in these accounts.
Okay.
That make sense?
So you were a late joiner, but you immediately got the things.
I got the state.
Okay.
And when I do that SAL and subscribe, it's an atomic command, which means give me the state as it's right now, and then any updates to that state come to me post the query.
Another example might be like Facebook. When you log into Facebook, you see the status updates you missed, and then do once they occur.
Okay. Got it.
Yeah. So SAL and subscribe, I can tell you this, is probably our most popular command that people execute because we have yet to see any other middleware that does this atomically the way we do it.
What's the NoSQL database that the person using for this?
Everything in AMPS is written by ourselves. We've written everything.
So you created your own.
We created a super ridiculously performant, lock-free, parallel database. Yes. That was a mouthful.
Yes.
Yeah, I have a new test case for you. So instead of tracking taxis, because there are very few taxis in New York, you should track kids. So it will be like a
Kids?
It will be like parents monitoring there. So they can see, oh, my kid is going there, my kid is going there.
Okay, so this is it.
That's the right test case.
Okay. Now I'm going to tease you with some goodness. So we all have where we come from in life. So I grew up as a kid into programming, but my father, God bless him, him and two other guys were the creators of something called GPS. And I remember as a kid, teenager, 16, 17, we were dreaming up applications that we could do with this. And one of them was to embed in every child, every kid, a GPS tracking device.
That's what I'm saying. So
The other problem was this was quite a long time ago, and they didn't have quite the devices. In fact, in 1987, my dad went over to China to try to find a manufacturing company to build a GPS watch, which I told him was a stupid idea. That's a dumb idea. Why would you ever do that? So he comes back and he says, the only problem is I'm 10 years too early. The electronics are not small enough yet. We're going to embed wearable GPS devices so parents can weave them into the fabric of their kids' coats and whatnot. Make sense?
Yeah.
So the cool thing about it is the reason it's different than a time series database, it's actually in a lot of ways more cool because it's only a time series for the things that move. So for example, if you had 1 million objects, but only 100 of them updated, you'd only have time series for the 100, not for the 1,000,000.
Like video conversion does the same thing. There are complete frames at a period of time.
Correct.
And it tracks your stuff as you go.
There's smart people everywhere.
Yes, sir.
Yeah.
What do you do for high availability? I know it's for financial services, so you must have something in there. Is it external with like load balancers and just sending it to everywhere, or what?
You know, we tell you don't go down. No.
Which
No,
was that
we-
easy?
Yeah. No, we have full replication capabilities, synchronous and asynchronous. You can combine the two, so you can have synchronous replication, asynchronous, and synchronous happening at the same time. You could have 5 synchronous replications and 5 asynchronous replications all at the same time. The replication is super cool because it's not like database replication. We are replicating the data and we are replicating it based on a topic and filter or set of topics and filters. So you can selectively replicate. So let's say that I wanted to replicate to Hong Kong and the only thing I want to send to Hong Kong are trades that have some attribute that would impact Hong Kong with the Hong Kong book, right? So they don't have to get every trade. They can only get the ones that they need. So we do selective topic and content filtered replication, synchronous and asynchronous. And then our client, okay, we have a client in C++, C, Python, C#, Java. Our clients are built with a store and forward capability and other H8 mechanisms where they store the bookmarks that you got on your subs and all that good stuff. So if you want to pick up where you left off, you can do all that stuff. So a lot of that we've already engineered into the product. So a lot of HA kind of capabilities. We unlike most middleware, we detect dupes. We detect them and handle them. So if you have a scenario where a publisher is on A, fails over to B, and then he actually 100 of his 200 messages actually made it over to B, but he never got an ACK. He comes on, he starts pumping in 0 through 200. 100 get recognized as dupes. So we have a lot of capabilities there.
As a follow-up on that,
Yeah.
Is this a scale out or a scale up kind of thing? Like
Well, we can
that
run on
system
a
you were
huge
talking
machine.
about, I'm guessing that's multiple
We
computers.
do. We have customers that run hundreds of instances of AMPS in a scale-out way because they want to partition what they do. You can do it any way you want. What our goal is to scale up as high as we can go, which is why we were
Scale out
testing.
has to be partitioned.
Well, you can replicate between instances. You can, yeah, absolutely. Right? You have to make them talk to each other and replicate to each other, but you can do that in a lot of different ways. There's lots of different ways to do that.
No, I know. It's just like you have things like it's not even in the same realm, but like Vertica, how you have multiple nodes and all of them have at least like 2/3 of the data or something.
We do not do that type of stuff. We're not trying to do that. We're doing something entirely different and easy and straightforward.
Yeah.
Most people that grab our product, the first thing they tell us is really easy to use. I couldn't believe it. I set it up and it just ran. It just worked, which is great feedback.
We have time for one more question.
And so we have no desire to actually pitch this to the New York City tax academy.
No desire.
No
some point. But no, we're not in the business of pitching it. We've spent a lot of time crafting this piece of infrastructure, and we want to apply it to as many problems as we can. So focusing on one is probably not the right way for us. We want to focus on many different problems. I think there's a myriad of problems out there, not in financial services, in other industries, that all have these types of problems. What's the current state? How do I get back? How do I back test from 3 hours ago? There's all kinds of problems that we're hoping that we solve with AMPS. And not only that, the content filtering is huge because in a mobile world, you do not want to bombard phones with messages that they just want to throw away. And so being very selective, like we see other infrastructure out there, internet-based pub sub systems, they're all topic-based, and they offer no selectivity, right? So if you want to be more selective, you have to pick a topic, right, that nobody else is using, but then the problem is it bifurcates really quick. It gets out of control. So which one do I subscribe to? This guy's doing orders, and this guy's doing orders plus, and this guy's doing, Japanese orders, and this guy's doing, tea orders, who knows what they are. I just want all orders where the product is tea.
You had your hand up over there, right?
Yeah.
Yeah, we can take one more question.
So, are there any limitations with the programming language interfaces, C++ versus Python?
No. All of the client-side code, even though it's in different languages, we've tried to make it look the same. So the Python looks as close as it can to be if I wrote a program in Java or I wrote a program in C++. We've tried to make the client pretty neutral, although it's language bound. The way you interact with AMPS from any of the languages is exactly the same.
And any limitations in terms of platforms for servers?
Server is Linux only, no Windows. Sorry.
For me?
It's a Linux only product. The amount of time that we put into the tuning and the performance part of it, we just don't want to spend the time doing that on multiple platforms. It doesn't make any sense. So concentrate our efforts. Yeah.
If we can take the last question.
Yeah.
If we had the resources, would you be confident your machine would be scalable as high-end as a T-wave, 400 qubits?
I'm pretty sure that from an engineering perspective, we could make this thing scale on just about anything. The level of engineering we've already put into the product is way beyond what other people put in. The number of algorithms we have on the fan-out side that do adaptive thread up and down, spin up, spin down, adaptively, the way we would do all that stuff, the way we get concurrency with some pipelining that we're doing, I think all of that plays out. I mean, we're going to great lengths when we come up, for example. We will move pages of memory around to get the right access patterns in terms of performance. I mean, there's a lot of stuff we're doing.
Okay, Jeffrey will be here for one-on-one questions for whoever did not get a chance to ask. Great big round of applause. Thank you, Jeffrey.